The closest star to our Sun is often described as a neighbor, a word that suggests something familiar, something within easy reach. In astronomical language, it truly does sit nearby, close enough that scientists refer to it as part of our immediate cosmic surroundings. And yet, within that quiet description lies a detail that gently unsettles our intuition. Alpha Centauri is not a single star, but a small family of three, bound together by gravity. One resembles our own sun, another glows with a softer orange hue, and the third, a faint red dwarf, flickers with bursts of energy, and happens to be the closest individual star to Earth. Over time, astronomers have identified planets moving around this distant system, worlds that exist just over 4 light-years away, some of which may hold the right conditions for liquid water, perhaps even for life. But the deeper story is not only about what exists there, it is about scale. The vast separations between these stars, the intensity of their activity, and the quiet realization that even our most advanced technology cannot yet bring us there. When we begin to understand these distances, the idea of something being nearby in the universe starts to change in a very profound way. If this kind of journey, one that slowly reshapes how you see the universe, feels meaningful to you, consider subscribing to the channel and continuing to explore with us. For now, settle in, take a moment, and let's begin. A nearest neighbor. The phrase brings to mind something simple and human. A quiet house just beyond a fence. A familiar face you might greet from a porch. Someone close enough that, in half a minute, you could walk over and borrow a cup of sugar without thinking twice. In everyday life, closeness means ease. It means access, convenience, a sense that distance is barely there at all. But when we turn that same idea toward the stars, something subtle begins to shift. Our nearest stellar neighbor, Alpha Centauri, is described in similar terms. Astronomers call it next door. Scientific literature places it within our cosmic backyard. Everywhere you look, the language suggests the same idea, that it is near. And yet, that sense of nearness is deeply misleading. If we were to launch the fastest spacecraft humanity has ever built in its direction today, the journey would stretch far beyond anything we can comfortably imagine. Not only would your great-great-grandchildren never witness its arrival, but neither would theirs. The voyage would take close to 7,000 years. By the time such a craft reached its destination, the civilization that sent it might be long gone, its history faded beyond recognition. To put that span into perspective, 7,000 years ago, writing had not yet emerged. The pyramids had not been built. Bronze was still a new and transformative technology. Everything we call recorded human history, every empire, every discovery, every life lived and remembered, would fit entirely within that single journey. This is the quiet paradox of Alpha Centauri. It appears close enough to see with the naked eye, a steady point of light in the night sky. Close enough that we have detected planets orbiting its stars. Close enough that we can imagine distant oceans under unfamiliar suns. And yet, it remains so far away that reaching it lies beyond anything we can realistically achieve in our lifetimes. The nearest star is, in a very real sense, not near at all. And once that realization settles in, it begins to reshape how we think about distance, about scale, and about our place in the universe. Consider the fastest object humanity has ever created, the Parker Solar Probe. A spacecraft designed to study our sun up close, uses gravity itself to accelerate to extraordinary speeds. As it dives toward the sun and swings around it, it reaches velocities that feel almost unreal. At its peak, it travels at around 430,000 miles per hour, a number so large it almost slips past comprehension. At that speed, You could circle the Earth in just a few minutes. It represents the very edge of what human engineering has achieved when it comes to motion through space. And even then, it is nowhere near fast enough. Now imagine turning at that extraordinary speed toward Alpha Centauri. Even at around 430,000 miles per hour, the fastest velocity any human-made object has ever reached. The journey would stretch across roughly 6,800 years. For the sake of understanding, we can simply call it about 7,000 years. 7 full millennia of uninterrupted travel, moving through a silent vacuum at a pace that would destroy ordinary materials if even the slightest atmosphere were present. That number has a way of quietly dissolving any optimism we might carry about interstellar travel. It reveals something uncomfortable: our greatest technological achievements, as remarkable as they feel, barely register when measured against the distances between stars. We have built machines that outrun nearly everything in the solar system, second only to light itself, and still, those machines would need longer than all of recorded human history just to reach the nearest star. There is another perspective that makes this even clearer. The spacecraft Voyager 1, launched in the late 1970s, has traveled farther than any human object ever created. For nearly half a century, it has been drifting outward, leaving behind the planets and crossing into interstellar space. Today, it sits about 15 billion miles from Earth, moving at roughly 38,000 miles per hour. At that steady pace, if it were somehow pointed toward Alpha Centauri, it would take more than 70,000 years to arrive. By then, it is difficult to say whether humanity, as we know it, would still exist. The idea of the mission itself might fade, be rediscovered, and fade again, repeating across cycles of civilization. This is what interstellar distance does to ambition. It reduces even our boldest accomplishments to something almost insignificant. Speeds that seem extraordinary from a human perspective become quietly inadequate when applied to the vast spaces between stars. We have crossed the solar system. We have placed machines on distant worlds. And yet, the nearest star remains just as unreachable as it was to the first people who looked up and wondered what those lights might be. The challenge, at its core, is not simply engineering. With enough time and resources, faster spacecraft could be imagined. The deeper limitation is written into the laws of physics themselves. The distances are so immense that even revolutionary technologies would still require lifetimes, or many lifetimes, to cross them. And then there is the ultimate boundary, the speed of light. Nothing with mass can exceed it. It is not just a practical limit, but a fundamental one. Light travels at about 186,000 miles every second, not per hour, but per second. In the brief moment it takes you to blink, light has already circled the Earth several times. It is the fastest motion the universe allows, the upper limit for anything that carries energy or information. And still, even at that speed, reaching Alpha Centauri takes time. Light itself requires a little over 4 years to make the journey, which means that the fastest possible message, the quickest signal we could ever send, would take more than 4 years just to arrive. There are many ideas in science fiction that attempt to bypass this limit. Warp drives, wormholes, shortcuts through space and time. But so far, none of these have found a place in real, testable physics. As far as we can tell, the speed of light is a boundary that cannot be crossed. When we translate that travel time into distance, the numbers begin to lose their meaning. Alpha Centauri lies about 4.37 light-years away. 1 light-year, in simple terms, is the distance light travels in a year, which is roughly 6 trillion miles. Multiply that out, and the separation becomes about 25 trillion miles. It is a number so large that it resists intuition. Written out fully, it stretches across 13 digits. If you tried to count to that number, 1 count per second, it would take close to 800,000 years to finish. Our minds were never designed to understand quantities like this. We evolved to track distances across landscapes, to remember locations within a few hundred miles, to count people, resources, and time in ways that mattered for survival. Trillions were never part of that experience. And so when we say that Alpha Centauri is close, what we really mean is something very different from anything we encounter in everyday life. Those 25 trillion miles between us and Alpha Centauri are not filled with stars or dust clouds in any familiar sense. They are, for the most part, almost completely empty. What scientists call the interstellar medium contains, on average, about one atom in a space the size of a small cube measured in centimeters. By comparison, the air you are breathing right now contains an almost unimaginable number of molecules in that same volume. Even the most carefully created vacuum on Earth would seem crowded when placed beside the vast emptiness between stars. This quiet void extends the entire distance. It is colder than anything we have ever directly experienced, darker than any night sky we can imagine, and emptier than any desert or ocean on our planet. There is no wind, no sound, no texture, only an immense stillness, occasionally interrupted by a lone hydrogen atom drifting through the dark. And this is considered a short journey. This is what astronomers mean when they say something is close. To make sense of these scales, we often turn to comparisons, not because they are perfect, but because they give our minds something to hold on to. Imagine, for a moment, shrinking the sun down to the size of a small basketball, just under 10 inches across. At that scale, Earth becomes something barely visible, a tiny grain of sand, only a couple of millimeters wide. The moon shrinks even further, becoming little more than a speck, circling less than an inch away from that grain. The entire inner solar system, from Mercury out to Mars, would fit comfortably inside a large room. Jupiter would roll somewhere far away, like a marble near the edge of a distant field. And Pluto, at its average distance, would drift roughly a mile from your small, glowing basketball sun. Now comes the difficult part. Where would Alpha Centauri be in this model? It would not fit in the room. It would not fit in the city. To keep the scale consistent, the nearest star would be another basketball placed about 4,400 miles away, roughly the distance between New York and Berlin. To include it, your simple model would need to stretch across an entire ocean. Even if we try again, reducing everything further, the result remains the same. Imagine Earth as a single grain of sand so small it could slip between your fingers. The moon would hover just a short distance away. The sun would become a beach ball far in the distance. Pluto would orbit miles from that tiny grain. And Alpha Centauri would still be thousands of miles away, a distant point somewhere far out in the ocean, far beyond anything that feels intuitively close. Shrinking the scale does not bring the stars closer. It only reveals how vast the separation truly is. We can also think in terms of movement. A person walking with purpose moves at about 3 miles per hour. At that pace, crossing a continent would take months. That same steady rhythm carried our ancestors across the world over generations. But walking to Alpha Centauri at that speed would take more than 500 billion years. The universe itself is only about 13.8 billion years old. The journey would require dozens of times the entire age of the cosmos. Even faster travel offers little comfort. Driving at highway speed, you could cross a continent in days. Reaching the moon would take months. Reaching the sun, ignoring the obvious impossibilities, would take well over a century. And reaching Alpha Centauri would still take tens of millions of years. Every comparison leads to the same quiet conclusion. No matter how we scale it, no matter how we imagine it, the nearest star remains profoundly distant. By the time such a journey finally ended, Earth itself would no longer be the world we recognize. Continents would have shifted into entirely new arrangements. Species not yet imagined would have appeared, thrived, and disappeared again many times over. Humanity, if it were remembered at all, might exist only as a distant trace in some forgotten record. Now consider something far more familiar. A commercial airplane moves at around 500 miles per hour. At that speed, a journey across the Atlantic takes only a handful of hours. It feels manageable, contained within a single day, something that fits comfortably within human experience. But extend that same speed outward, toward Alpha Centauri, and the scale quietly transforms. The journey would take on the order of 5.7 million years. And if, somehow, descendants of the original travelers were to arrive, they would not resemble us in any meaningful sense. Evolution over millions of years would reshape them entirely. For context, only a few million years separate modern humans from our shared ancestors with chimpanzees. The beings that reached that distant system would be as unfamiliar to you as those early ancestors are to us now. At some point, every comparison begins to fail. Every analogy reaches its limit. The distances involved simply do not align with the way human intuition works. We are not built to understand scales like this. Our instincts were shaped by a much smaller world. Distances measured in valleys, in rivers, in journeys between villages. The longest travels took months, perhaps years, and the farthest places could still be reached within a lifetime or a few generations. Everything that mattered existed within a relatively small horizon. The universe does not follow those rules, and Alpha Centauri, despite being the nearest star, makes that reality unmistakably clear. Perhaps the most surprising part is how easily we can see it. On a clear night, from the right parts of Earth, you can simply look up and find it. A bright point in the constellation Centaurus, one of the most luminous stars in the sky, outshone only by a couple of others. It has been known to human eyes for thousands of years. Ancient cultures mapped its position, gave it meaning, wove it into their stories. Even now, you can watch it shimmer gently through the atmosphere, capture it with a simple camera, or hear a child ask what that bright point might be. And yet, the light reaching your eyes in that moment has been traveling for more than 4 years. It has crossed an immense stretch of darkness, covering tens of trillions of miles before arriving at that exact instant. With modern instruments, we have learned to read that light in extraordinary detail. Telescopes break it apart, revealing the chemical makeup of the stars and the temperatures of their surfaces. Careful observations track their motion over time, allowing us to understand how they orbit one another. By combining signals from multiple observatories, scientists can resolve structures within the system that once seemed impossibly distant. We can see so much, and yet we remain so far away. We now understand a surprising amount about this nearby system. Alpha Centauri A appears remarkably similar to our own Sun, almost like a familiar reference placed in an unfamiliar setting, its companion. Alpha Centauri B burns a little cooler and dimmer, giving off a softer orange glow. And then there is Proxima Centauri, the closest individual star to Earth, a small red dwarf that behaves far less gently, releasing powerful flares that far exceed anything our Sun typically produces. Over time, we have traced their motions, measured their masses, estimated how old they are, and even projected how they may evolve in the distant future. And perhaps most remarkably, we have discovered planets within this system. In the year 2016, astronomers confirmed the presence of a world roughly similar in size to Earth, orbiting Proxima Centauri, within a region where liquid water could, in principle, exist. It became the closest known exoplanet, quietly orbiting the nearest star beyond our Sun. Since then, additional worlds have been identified, gradually expanding our picture of what exists just beyond the edge of our solar system. And yet, this knowledge carries a certain tension. We can see where such worlds are. We can describe them, model them, even imagine what their surfaces might be like. But we cannot reach them. It is a little like standing outside a room with a clear window. You can look inside and observe everything in detail. You can describe the arrangement, count the objects, understand how the space is organized, but the door remains closed. No matter how clearly you see, you cannot step inside. Alpha Centauri feels like that distant room. We continue to study it, carefully cataloging what we can observe, knowing that, for now, it remains out of reach. The stars continue their slow orbits. The planets circle quietly around them. Whatever processes unfold there do so without any direct human presence. We know where to go, we simply cannot go there. And what makes this even more striking is that Alpha Centauri is not just one nearby system among many. It is the closest across the entire Milky Way. Among hundreds of billions of stars spread over distances so vast that light itself requires tens of thousands of years to cross them. There is no star system nearer to us than this one. It is worth pausing on that idea. Hundreds of billions of stars, scattered across a galaxy of immense scale. And yet the nearest one still lies so far away that reaching it remains beyond us. The universe, it seems, keeps its distances. Even the very closest star demands a journey of nearly 7,000 years at the highest speeds we have ever achieved. And beyond it, the distances only grow. Barnard's star, a faint red dwarf, lies about 6 light-years away. Wolf 359, known in part through science fiction, sits even farther. And Lalande 2185 drifts beyond that still. Each step outward adds thousands upon thousands of years to any possible journey. If Alpha Centauri already feels unreachable, then these more distant stars recede even further into abstraction. Within roughly 10 light-years, we find the only stars that could be considered even remotely within reach of any future technology we can realistically imagine. Beyond that small region, the rest of the galaxy begins to feel less like a destination and more like a separate reality altogether. This separation is not accidental. It is part of how the universe is structured. Stars are not just far apart. They are separated by distances so immense that crossing them requires either accepting journeys measured in millennia or discovering entirely new physics that we do not yet understand. In our region of the Milky Way, the average spacing between stars is about 4 light-years. Alpha Centauri happens to be slightly closer than that, a small cosmic coincidence that makes it our nearest neighbor. But even this closer-than-average distance still translates into trillions of miles of near-perfect emptiness. Each star system exists in quiet isolation. Vast gaps separate one from another, gaps so large that even light needs years to cross them. And if there are other civilizations, on distant worlds orbiting other suns, they would face the same constraints, the same speed limit, the same immense separation. In that sense, the universe does not favor connection. It allows it only under very strict conditions. Alpha Centauri, sitting at the smallest possible distance between stars, shows us that even the shortest gap remains beyond our reach for now. And then there is something even more subtle. The light you see from Alpha Centauri tonight did not leave that system just now. It began its journey more than 4 years ago. By the time it reaches your eyes, it is already carrying the past. This is one of the quiet truths of astronomy. We never see distant objects as they are in the present. We see them as they were, preserved in light that has been traveling across space. When you look at Alpha Centauri, you are looking 4 years back in time. The photons arriving at your eyes began their journey while entirely different moments were unfolding here on Earth. Events that once felt immediate have already passed. Lives have changed. New ones have begun. In a very real sense, Alpha Centauri exists in a different present than we do. If something dramatic were to happen there right now, we would not know for years. The information is already on its way, carried by light moving at the fastest speed the universe allows, still crossing that vast distance of darkness before it can reach us. And until it does, the present of that distant system remains hidden, quietly unfolding beyond our view. Whatever is happening at Alpha Centauri right now remains hidden from us for years to come, and any attempt at communication would face the same quiet delay. If humanity sent a message today, carried by radio waves moving at the speed of light, it would take about 4 years and 4 months just to arrive, and any reply sent immediately would require the same time to return, creating a minimum round trip of roughly 8 years, a span that makes real conversation impossible, where no exchange feels immediate and every response arrives long after the original thought has passed. This separation in time is not unique to Alpha Centauri. It is a universal feature of how we observe everything beyond our world. The moon appears as it was just over a second ago, the sun as it was several minutes in the past, and Jupiter as it was tens of minutes earlier, depending on where it sits in its orbit. And as distance increases, so does this delay, stretching further and further into the past. Proxima Centauri appears as it was a little over 4 years ago, while the Andromeda Galaxy shows us a version of itself from millions of years in the past. And the most distant objects we can detect reveal a universe that existed billions of years ago. A universe that may no longer look the way we see it now. Even our nearest stellar neighbor exists on its own timeline, separate from ours. The Alpha Centauri system we observe tonight has already lived through more than 4 years of change that we have not yet seen. Its stars have turned. Its planets have continued their paths. Storms may have formed and faded. Flares may have erupted into space. And all of it remains unseen until the light carrying those moments completes its long journey to us. In this way, the universe does not allow a shared present across vast distances. There is no single moment experienced together between Earth and Alpha Centauri. Only the past we can observe and a future we have yet to receive. And yet, despite these immense separations, we have still managed to learn an extraordinary amount, drawing detailed knowledge from faint light that has traveled for years before reaching us, mapping the system with a level of precision that would have seemed almost impossible not long ago. What we have discovered quietly challenges the simplicity of what we see in the sky. That single bright point of light is not one star at all. Even a modest telescope reveals that it separates into 2 distinct stars, 2 separate sources of light bound together in motion. But the story does not end there. A third star exists farther out, too faint to be seen with the naked eye, hidden from human awareness for centuries after the brighter pair had already been studied. This third member, known as Proxima Centauri, sits slightly closer to Earth than the other 2, making it the nearest individual star to our solar system. A quiet reminder that even our closest neighbor held secrets for much of human history. Together, these 3 stars form a gravitationally bound system, orbiting one another over spans of time that extend far beyond anything familiar. Each one a fusion-powered sphere of light, slowly tracing paths that have continued for billions of years and will continue long after our own time has passed. To truly understand what exists, there requires stepping outside everyday intuition, because the scales involved, both in distance and time, belong to a different kind of reality. What appears as a single point in the night sky is, in truth, a complex and evolving system, where multiple stars move together in a slow and silent dance, unfolding across timescales that make a human life feel almost momentary. For thousands of years, every person who looked up at Alpha Centauri believed they were seeing a single star. Shepherds watching the sky through changing seasons saw one steady point of light. Philosophers mapping the heavens recorded it as one object, and medieval astronomers used it for navigation as if it were simple and singular, across generations, across centuries. That bright presence appeared unchanged, a single star in a quiet part of the sky. But that understanding was not complete. In the late 17th century, a French Jesuit priest named Jean Richaud was observing a comet from Puducherry in India, and as the comet passed near that familiar star, he turned his telescope toward it. What he saw, almost by accident, reshaped what we thought we knew. The single point of light separated into two. Where the eye had always seen one star, the telescope revealed a pair, two distinct sources of light, two stars orbiting one another, close enough to appear unified from Earth, yet clearly separate when magnified. This discovery placed Alpha Centauri among the earliest known binary systems, joining a small group of stars that had revealed their dual nature. It showed that stars were not always solitary, that they could exist in gravitational partnerships, moving together through space. And yet, even this was not the full picture. It would take another 2 centuries before astronomers realized there was more still hidden within that same point of light. A third star existed at the outer edge of the system, so faint that it escaped detection despite careful observation of the sky. This distant companion, now known as Proxima Centauri, turned out to be slightly closer to Earth than the brighter pair, quietly holding the title of our nearest stellar neighbor while remaining invisible to the naked eye. So what once appeared simple was, in reality, a system of 3 stars, each powered by nuclear fusion, each bound together by gravity, moving in a slow and complex dance that has continued for billions of years, all of it concealed within what seemed, for most of human history, to be a single flickering point. The story of Alpha Centauri reflects something broader about how we come to understand the universe. Knowledge unfolds gradually. Early astronomers recorded its position and brightness, treating it as a fixed point on a celestial sphere, because there was no reason to suspect otherwise. Even its name evolved slowly, shaped by different cultures over time, originating from older traditions that described it as part of the figure of a centaur, before eventually becoming the designation we use today. The moment Richaud observed its dual nature marked a turning point. It suggested that stars could form systems, that they could orbit shared centers of mass, that they were not scattered randomly but could exist in structured relationships. This realization opened the way to a deeper understanding of stellar physics and cosmic architecture. But knowing that Alpha Centauri was a binary system still left a crucial question unanswered. How far away was it, really? Answering that required a level of precision that would not be possible until much later. When astronomers began to measure the smallest shifts in a star's position as Earth moved through space, slowly revealing the true scale of the distance between us and our nearest neighbor. This method, known as stellar parallax, is surprisingly simple in principle. If you hold your thumb out in front of you and close one eye, then the other, your thumb seems to shift against the background. The effect comes from viewing it from 2 slightly different angles. In the same way, a nearby star appears to move ever so slightly against more distant stars when observed from opposite sides of Earth's orbit, separated by about 6 months. For Alpha Centauri, that shift was almost impossibly small. Henderson measured a motion of less than 1 arcsecond, a fraction of a degree so tiny it is comparable to the width of a human hair seen from several meters away. Detecting such a subtle movement required extraordinary precision, pushing the instruments of the 19th century to their limits. When Henderson calculated the distance from this measurement, he hesitated. The result suggested something remarkable, that Alpha Centauri was closer to Earth than any other star. It was an extraordinary claim, and one that carried risk. If the measurement were wrong, it could damage his credibility. So he delayed, refining his data, questioning his results, and waiting for certainty. Meanwhile, in the late 1830s, another astronomer, Friedrich Wilhelm Bessel, successfully published a parallax measurement for a different star, proving that the method worked and that stars lay at vast distances measured in light years. Only then did Henderson feel confident enough to share his own findings. In the year 1839, he published his results, confirming that Alpha Centauri was indeed the nearest star system, located a little over 4 light-years away. It was an answer to a long-standing question, one he had nearly kept to himself for too long. The final piece of the story emerged in the early 20th century. In 1915, Robert Innes, working in South Africa, noticed a faint red star moving through space in a way that closely matched the motion of Alpha Centauri. Such alignment was unlikely to be a coincidence. He proposed that this dim object was not separate, but part of the same system, orbiting the brighter pair from a great distance. Further analysis revealed something even more intriguing. This faint star was actually slightly closer to Earth than the other two. Innes named it Proxima Centauri, from a word meaning nearest, recognizing that he had identified the closest individual star to our solar system. With that, the picture became complete. What once seemed like a single point of light was revealed as a system of 3 stars, bound together by gravity and moving through space in a slow, intricate pattern that unfolds over timescales far beyond human experience. Within this system, Alpha Centauri A stands out as the dominant star. It is larger, more luminous, and in many ways strikingly similar to our own Sun. Astronomers classify it as a G-type main-sequence star, the same category as the Sun, which means it shares comparable surface temperatures, similar chemical composition, and the same fundamental process of nuclear fusion at its core. Measured more precisely, it contains slightly more mass than the Sun and radiates noticeably more energy, shining brighter while maintaining a familiar yellow-white appearance. In many respects, it feels like a distant reflection of the star that sustains life on Earth, a reminder that even in an unfamiliar system, there are elements that remain quietly recognizable. In terms of size, Alpha Centauri A closely mirrors our own Sun. It spans a little over 1 solar diameter, measuring roughly 865,000 miles across, large enough to contain more than 1 million Earths within its volume. Like our Sun, it is a sphere of hydrogen and helium plasma, with a core so hot and dense that atomic nuclei fuse together, releasing energy that slowly makes its way outward as light and warmth. Its age also aligns closely with our own star, estimated at around 4.85 billion years, placing both within the same broad era of cosmic history. If Earth could somehow be moved into orbit around Alpha Centauri A at the same distance we currently maintain from the Sun, the experience might feel surprisingly familiar. The light would be slightly brighter, the star itself appearing a little larger in the sky, but the fundamental sensation of daylight, of warmth on your skin, of blue skies and golden evenings, would remain recognizable. This similarity is part of what makes Alpha Centauri so compelling. Among the hundreds of billions of stars in our galaxy, very few resemble the Sun so closely. To find such a star so nearby is, in a sense, a fortunate coincidence. It raises a quiet possibility that the conditions which allowed life to emerge here might not be entirely unique. Alongside it, Alpha Centauri B offers a gentle contrast. Slightly smaller, cooler, and less luminous, it still functions as a stable star, capable of supporting planetary systems and driving the chemistry needed for complex environments. Classified as an orange dwarf, it carries less mass than its larger companion, which leads to lower pressures and temperatures at its core, and in turn, a slower rate of nuclear fusion. As a result, it emits less energy, about half the luminosity of the Sun, and its surface temperature is somewhat cooler. This difference, though not extreme, subtly alters the character of its light. Instead of the familiar yellow-white glow, Alpha Centauri B shines with a warmer, more orange tone. On a planet orbiting this star, daylight would feel slightly different, softer, with shadows carrying faint amber hues, giving the landscape an atmosphere that is both familiar and quietly unfamiliar at the same time. Despite these differences, Alpha Centauri B still possesses a habitable zone, a region where temperatures could allow liquid water to exist, because the star is dimmer. This zone lies closer in than Earth's orbit around the Sun, but within that range, a planet could receive a comparable amount of energy. Together, Alpha Centauri A and B create a unique environment. From the surface of a planet orbiting either star, the other would appear as an exceptionally bright object in the sky, far more luminous than any star we see from Earth. The presence of two suns, each with slightly different colors, would produce lighting conditions unlike anything in our experience. A subtle blend of hues shifting across the sky, reminding any observer that they are part of a system far more complex than our own. Proxima Centauri completes this system, but in a way that feels entirely different from its brighter companions. It is a small red dwarf, one of the smallest types of stars capable of sustaining nuclear fusion in its core, classified deep within the red dwarf category. It sits at the very lower edge of what we would still call a true star, any smaller, and it would not generate enough pressure and heat to ignite fusion at all, becoming what astronomers describe as a failed star. Its mass is only a small fraction of the Sun's, so light that even gathering several of them together would still not equal the mass of a single sun. And this low mass defines everything about it. Proxima does not shine brightly. In fact, its energy output is astonishingly faint. You would need hundreds of stars like Proxima combined just to match the light of our Sun, and even more to rival Alpha Centauri A. Its size reflects this as well. Proxima is only a small portion of the Sun's diameter, not much larger than Jupiter, the biggest planet in our solar system. If you could place them side by side, the difference would feel surprisingly small, blurring the line between what we think of as a star and what we think of as a planet. Its surface is much cooler too, glowing at a temperature far below that of the Sun. This cooler surface gives Proxima its deep red color, and much of its energy is emitted in wavelengths we cannot see. To human eyes, its light would feel dim and reddish, creating an environment that would seem unfamiliar, almost subdued compared to the bright daylight we know. And yet, beneath this quiet appearance lies something far more intense. Proxima is not a calm star. It is highly active, driven by powerful magnetic forces that extend throughout its entire structure. Unlike the Sun, where convection happens mainly near the surface, Proxima is in constant motion from its core all the way outward. This continuous churning generates strong magnetic fields across much of its surface. From time to time, those magnetic fields release energy in sudden bursts known as stellar flares. When this happens, the star can brighten dramatically in a matter of seconds, releasing energy far beyond what our Sun typically produces. These eruptions make Proxima a far more volatile environment than its dim appearance might suggest. Despite its small size and restless nature, Proxima holds a quiet distinction. It is the closest individual star to our solar system, slightly nearer than the two brighter stars we can easily see. For most of human history, it remained completely unnoticed, hidden in plain sight simply because it was too faint to detect without careful observation. It was only in the early 20th century that its presence was confirmed, revealing that our nearest neighbor was not the bright pair long observed, but this small, dim star moving quietly alongside them. All this time, it had been there, orbiting at a great distance, part of the same system, waiting to be recognized. Meanwhile, the two brighter stars continue their slow motion around one another. Alpha Centauri A and B orbit a shared center of mass over a period of nearly 80 years, meaning a full cycle takes most of a human lifetime. Their path is not a perfect circle, but an elongated shape, causing the distance between them to change significantly over time. At their closest approach, they draw near at a distance comparable to the span between our Sun and Saturn. At that point, their gravitational interaction becomes especially strong, each star subtly influencing the other as they continue their long, measured dance through space. At their greatest separation, known as a pastron, the two stars drift far apart, reaching a distance comparable to the span between our Sun and Pluto. In this phase, they are several times farther from each other than at their closest approach, tracing out a wide and elongated path that repeats over decades. For an observer within the system, this changing distance would shape the sky in subtle but remarkable ways. Imagine standing on a planet orbiting Alpha Centauri A. When the two stars draw near, Alpha Centauri B would shine with striking intensity, appearing far brighter than any planet we see from Earth. It would cast soft shadows, add a faint warmth, and dominate the night sky with a steady, luminous presence. As time passes and the stars move apart, that same companion would slowly retreat, becoming less overwhelming, though still the brightest point in the sky after the primary star. This gradual shift would unfold over decades, a slow and graceful motion that could be observed across a lifetime. These movements are not just visual curiosities, they influence the very structure of the system. The gravitational pull between the two stars affects where planets can exist safely. Simulations suggest that stable planetary orbits are possible, but only within certain regions. Around each star, planets must remain relatively close to avoid being disturbed by the gravitational influence of the other. Beyond those limits, orbits would become unstable over long periods. A planet might be pushed outward and lost to space, or drawn inward toward its star. In this way, the system creates natural boundaries, regions where planets can persist, and others where stability is unlikely. Fortunately, the regions where liquid water could exist, the so-called habitable zones, fall well within these stable areas for both stars. This means that, at least in principle, rocky planets with suitable conditions could orbit either star without being disrupted. While a full orbit between Alpha Centauri A and B takes nearly 80 years, a span comparable to a human lifetime, it is only a brief moment on cosmic time scales over billions of years. The two stars have circled each other tens of millions of times, repeating the same slow pattern again and again, a rhythm that will continue long into the future. Far beyond this central pair, Proxima Centauri follows its own distant path. It orbits the system at a separation so vast that it challenges even the scales we have already considered. The distance between Proxima and the inner pair is thousands of times greater than the distance between Earth and the Sun, stretching across an expanse so large that even light requires weeks to travel from one to the other. At its current separation, a beam of light would take more than 2 months to cross that gap, even within a single star system. Distances of this magnitude remind us how quickly space expands beyond familiar intuition. Proxima's orbit is equally immense in time. It takes on the order of hundreds of thousands of years to complete a single circuit around its brighter companions. The last time it occupied its current position, modern humans had not yet appeared. Since then, our species has emerged, developed language, built civilizations, and begun to explore space, all within just one of Proxima's slow revolutions. Over the lifetime of the system, this distant star has completed only a few thousand such orbits, each one stretching far beyond the span of human history, for many years after its discovery. Astronomers were uncertain whether Proxima truly belonged to the system or was simply passing nearby. The vast distance between it and the central pair made this difficult to determine. But with more precise measurements, that uncertainty has faded. The motion of Proxima reveals that it is indeed bound by gravity to Alpha Centauri A and B, forming a true triple system, quietly held together across distances that seem almost impossible to reconcile with the idea of a single stellar neighborhood. The three stars form a true triple system, with Proxima following a vast and distant path around the central binary over spans of hundreds of thousands of years. This layered structure is what gives the system its long-term stability. Proxima orbits so far away that, from its perspective, the two central stars behave almost like a single combined mass. Their shared motion around a common center effectively smooths out when viewed from such a distance. This wide separation avoids the complicated three-body interactions that could otherwise disrupt the system over time. If Proxima were much closer, the gravitational pull between all three stars would become chaotic, eventually pulling the system apart. Instead, the immense distance between Proxima and the inner pair allows each star to move along its path with minimal disturbance. Our own sun will not last forever. In about 5 billion years, it will exhaust the hydrogen in its core, expand into a red giant, and eventually shed its outer layers before settling into a white dwarf. Alpha Centauri A is expected to follow a similar path on a similar timeline. Stars like these shine brightly, but only for a limited period when viewed on cosmic scales. Proxima Centauri, however, exists on an entirely different timeline. Red dwarf stars burn their fuel at an incredibly slow rate, allowing them to shine for trillions of years, not billions, but trillions, a scale that stretches far beyond anything we can easily grasp. The universe itself is only about 13.8 billion years old, encompassing everything from the first galaxies to the emergence of life on Earth. All of that history fits within that span. And yet Proxima is expected to continue fusing hydrogen for at least 4 trillion years, and possibly far longer. This means it has used only a tiny fraction of its total lifespan so far, despite already existing for billions of years, when our sun has long since faded. Proxima will still be shining. Even after stars like the sun have disappeared across the universe, Proxima will continue to burn, enduring for hundreds of times longer than the current age of the cosmos. For any planets that orbit it, this creates an extraordinary possibility. Life on Earth has had only a few billion years under relatively stable conditions. But around a star like Proxima, the window for evolution could extend almost indefinitely. Trillions of years of steady energy would allow processes to unfold on timescales that make Earth's biological history feel brief by comparison. In that sense, red dwarfs like Proxima may be the true long-term inhabitants of the universe. The bright stars we easily see will fade relatively quickly, while these dim, steady stars continue on quietly through the deep future. When we compare the Alpha Centauri system to our own solar system, both similarities and striking differences begin to emerge. Our system stretches from Mercury, orbiting close to the Sun, all the way out to the distant Oort cloud, far beyond the planets. Its overall size is comparable to the immense distance between Proxima and the central pair in Alpha Centauri. But the way mass is distributed is entirely different. In our solar system, nearly all of the mass is concentrated in the Sun itself. Everything else, planets, moons, asteroids, and comets, makes up only a tiny fraction of the total. The Sun dominates gravitationally, and all other objects simply follow its influence. In contrast, Alpha Centauri divides its mass between 3 significant stars. Alpha Centauri A carries slightly more mass than our Sun, Alpha Centauri B somewhat less, and Proxima adds a smaller but still meaningful contribution. Together, they form a system with more than twice the mass of our Sun, spread across multiple bodies. This shared distribution creates a level of gravitational complexity far beyond what we experience in our own solar system. Planets moving around Alpha Centauri. A cannot simply orbit in isolation. They must constantly respond to the gravitational influence of Alpha Centauri B. Farther out, objects begin to feel the pull of all three stars at once, creating a system where orbital paths are shaped by multiple competing forces. Predicting these motions with accuracy requires detailed computer simulations, as the interactions become too complex for simple calculations. This same complexity also affects how planets might have formed in the first place. The presence of multiple stars could have disrupted the disks of gas and dust where planets are born, preventing material from gathering into larger bodies. But it is also possible that this gravitational interplay had the opposite effect in certain regions, concentrating matter and encouraging the formation of planets in specific zones while limiting it elsewhere. For many years, this uncertainty led astronomers to question whether such a system could support planets at all. Then, in the year 2016, that uncertainty shifted. Astronomers confirmed the existence of a planet orbiting Proxima Centauri, a world similar in size to Earth. Located within the habitable zone of the closest star to our solar system, it became the nearest known exoplanet, quietly orbiting right next door in cosmic terms. Since then, additional planets have been identified around Proxima, showing that even within such a dynamically complex environment, worlds can and do form. And yet, the conditions on these planets are unlike anything we experience in our own system. The intense flare activity of Proxima Centauri, the possibility of atmospheres being stripped away by high-energy radiation, and the unusual light from a red dwarf star that emits much of its energy beyond human vision all create an environment that feels both familiar and deeply alien. The planets are there. The question is whether anything could live on them. On August 24, 2016, the European Southern Observatory announced this discovery after careful analysis and review, confirming that a planet truly existed around Proxima Centauri, not just any planet, but one comparable in size to Earth, positioned within a region where liquid water might be possible. The announcement carried significant weight. For decades, scientists had debated whether planets could even form in the Alpha Centauri system. Given its complex gravitational structure, many expected that, even if planets existed, the habitable zones might remain empty. But that expectation did not hold. Proxima Centauri B, as the planet came to be known, orbits at a distance where temperatures could allow liquid water. Provided the atmosphere is suitable, its mass suggests a rocky composition, not unlike Earth, and it lies just over 4 light-years away, closer than any other known world beyond our solar system. The discovery naturally led to speculation about life. If a potentially habitable planet exists at the nearest possible destination, it raises the possibility that life might have emerged there as well. For a moment, it seemed as though the universe had placed an Earth-like world within reach. But as the data was examined more carefully, that sense of optimism became more uncertain. The same observations that confirmed the planet also revealed the nature of its host star, a small red dwarf with a far more violent character than its size might suggest. And that changes the question entirely, from whether such a world exists to whether it could truly remain habitable at all. The question that followed that announcement in 2016 has not been resolved even now. Could life truly survive on a planet orbiting Proxima Centauri? The answer, it turns out, is far more complex than it first appeared. Proxima Centauri. B orbits its star at a distance that feels almost impossibly close when compared to our own solar system. It lies at about 0.05 astronomical units from its star, whereas Mercury, the innermost planet around our Sun, orbits at roughly 0.4. This means Proxima B sits many times closer to its star than Mercury does to ours, a proximity that reshapes everything about its environment. Because of this, its orbital period is strikingly short. The planet completes a full orbit in just over 11 days, meaning a full year. There lasts less than 2 weeks by our measure. Time, in that sense, would feel very different. Any seasonal changes, if they exist at all, would pass rapidly, cycling in days rather than months. The way this planet was discovered is also worth considering. Astronomers did not see it directly at first, but instead detected a subtle motion in the star itself. As Proxima B orbits, its gravity gently pulls on the star, causing it to move in a small, repeating pattern. This motion can be measured through tiny shifts in the star's light, allowing scientists to infer the planet's presence, its orbital period, and a minimum estimate of its mass. For Proxima B, that minimum mass is just slightly greater than Earth's, suggesting a rocky composition and a surface gravity not too different from what we experience. The true mass may be somewhat higher, depending on how its orbit is tilted relative to our view, but even the minimum value tells us something important. This is not a gas giant, nor an icy world like Neptune. It is, by all indications, a solid planet, similar in scale to our own. And it resides within what is known as the habitable zone. This is the region around a star where temperatures could allow liquid water to exist on a planet's surface. Sometimes described as a balance, where conditions are neither too hot nor too cold. The exact boundaries of this zone depend entirely on the brightness of the star. More luminous stars push this region outward, while dimmer stars draw it inward. Proxima Centauri is extremely faint compared to the Sun, emitting only a tiny fraction of its energy. As a result, its habitable zone lies very close to the star itself. Calculations suggest that planets within a narrow range of distances could, in principle, maintain liquid water, and Proxima B falls comfortably within that range. At first glance, this seems promising. A rocky planet, similar in size to Earth, located in the habitable zone of the nearest star. But as we look more closely, the picture becomes far less certain and far more intriguing. Proxima B receives roughly 65% of the energy that Earth gets from the Sun. At first, this might suggest a frozen world, but the reality is more nuanced. On Earth, our atmosphere traps heat and raises the surface temperature significantly above what bare rock would experience. A similar effect on Proxima B, perhaps from a thicker atmosphere or stronger greenhouse gases, could raise temperatures enough to allow more moderate conditions. Without any atmosphere, estimates suggest a surface temperature of around -38 degrees Fahrenheit. Cold, but not beyond comparison. Mars, for example, has a similar baseline and still shows signs that liquid water once existed. With the right atmospheric balance, Proxima B could be temperate, perhaps even relatively warm. This possibility, a nearby world with Earth-like conditions, created a surge of excitement when it was first announced. But that initial optimism quickly met a more complex reality. The planet's close orbit introduces a powerful effect known as tidal locking, something that would fundamentally shape its environment. Tidal locking happens when gravitational forces slow a planet's rotation until one side always faces its star. Our own moon is a familiar example, showing the same face to Earth while the other side remains hidden. Proxima B, orbiting so close to its star, has almost certainly experienced this process. Over billions of years, its rotation would have gradually slowed until it became locked in place. This creates a world divided into two extremes. One side faces the star constantly, bathed in a steady red glow, while the other side remains in permanent darkness. There is no sunrise, no sunset, no cycle of day and night, only continuous light on one hemisphere and endless night on the other. The consequences for temperature could be severe. The day side receives constant energy with no cooling period, allowing heat to build continuously. The night side, in contrast, loses heat without any source of replenishment, potentially becoming extremely cold. This contrast creates a sharp gradient across the planet, unlike anything we experience on Earth. Here, our atmosphere and oceans help distribute heat, smoothing out temperature differences and maintaining a relatively stable climate. On a tidally locked world like Proxima B, that balance may not exist. Some models suggest the day side could become intensely hot, while the night side drops to extreme cold, far beyond familiar conditions. Between these two extremes lies a narrow region, the boundary where day meets night. In this zone, often called the terminator, light would remain in a constant state of twilight. Temperatures there could be more moderate, potentially allowing liquid water to exist. This region would form a continuous ring around the planet, a thin band where conditions might be more stable. If life were to emerge on such a world, it might be limited to this narrow region, existing in a place where the sun never fully rises and never fully sets. And yet, there is still uncertainty. Some models suggest that if the planet has a sufficiently dense atmosphere, winds and circulation could redistribute heat more effectively, softening the extremes between the two sides and expanding the regions where life might persist. So even here, the picture remains open, balanced between possibility and limitation, shaped by factors we are only beginning to understand. A sufficiently dense atmosphere could change this picture in important ways, allowing heat to circulate more effectively and making larger regions of the planet potentially habitable. Not just the narrow band between light and darkness. There is also the possibility that Proxima B is not perfectly tidally locked. If its orbit is slightly elongated beyond a certain threshold, it might instead settle into a resonance similar to Mercury, rotating 3 times for every 2 orbits around its star. In such a case, the planet would experience a form of day and night, though nothing like what we know on Earth. The sun might move slowly across the sky over many days, creating long and unfamiliar cycles of light and shadow. For now, this remains uncertain, as current observations are not precise enough to determine the exact rotational state, even under the most optimistic assumptions. However, the environment would still feel profoundly different, whether defined by endless daylight, permanent darkness, or a slow and unusual rhythm that unfolds over weeks. Yet tidal locking may not be the greatest challenge. The more serious concern lies with the star itself. Proxima Centauri is one of the most active flare stars known, and its behavior introduces conditions that could make survival extremely difficult for any nearby planet. Unlike the Sun, where much of the interior remains relatively stable, Proxima is in constant motion throughout its entire structure. Hot plasma rises and falls from its core to its surface, generating strong magnetic fields across a large portion of the star. This continuous activity leads to frequent and intense bursts of energy. At any given time, a significant portion of its surface may be magnetically active, far more than what we observe on the Sun. Even during periods of peak activity, these magnetic fields occasionally release their stored energy in sudden eruptions known as stellar flares, where twisted field lines reconnect and unleash powerful radiation and streams of charged particles. While our Sun produces flares, those from Proxima can be vastly more intense. In one observed event in the late 2010s, the star released a burst of energy so strong that its brightness surged dramatically across multiple wavelengths. For a brief moment, it emitted thousands of times more ultraviolet radiation than usual. Although such events may last only seconds, their impact on a nearby planet could be severe. The energy reaching Proxima B during such a flare would far exceed anything Earth typically experiences. And these eruptions are not rare. Smaller flares occur frequently, while larger ones happen on a regular basis. Over billions of years, This continuous exposure to radiation would shape the planet's environment in profound ways, raising an important and still unanswered question. Even if the conditions for liquid water exist, could anything endure under a sky that never truly rests? The consequences for Proxima B could be quite severe. Even under relatively calm conditions, the planet is exposed to far more high-energy radiation than Earth. It receives many times the extreme ultraviolet radiation we experience, along with vastly higher levels of X-rays. This kind of radiation can break apart biological molecules, ionize atmospheric gases, and trigger chemical reactions that may prevent complex organic systems from forming or surviving. During large flare events, the situation becomes even more intense. Radiation levels can surge dramatically, delivering bursts of energy that would overwhelm the surface environment in moments. Any life exposed directly would likely not endure such conditions for long. But beyond the immediate effects, the deeper concern lies in what happens to the atmosphere over time. High-energy radiation strips electrons from atoms in the atmosphere, turning them into charged particles. Once ionized, these particles become vulnerable to the stellar wind, a steady stream of charged material flowing outward from the star over long periods. This wind can gradually carry atmospheric gases away into space, thinning or even removing the protective envelope a planet depends on. In the case of Proxima Centauri, the stellar wind appears stronger than that of our Sun, and when combined with frequent flaring, the rate of atmospheric loss could be significant. Some studies suggest that over billions of years, this process might strip away most, if not all, of the original atmosphere. The implication is difficult to ignore. A planet may sit at just the right distance for liquid water, yet lack the very atmosphere required to sustain it. And still, the question is not fully settled. There are reasons to consider that habitability might persist under certain conditions. One possibility is the presence of a strong magnetic field. On Earth, our magnetic field acts as a shield, deflecting charged particles from the solar wind and helping preserve the atmosphere. If Proxima B has a similar internal dynamo, it could reduce atmospheric loss significantly. Another factor is geological activity. Planets can replenish their atmospheres through volcanic outgassing, releasing gases from their interiors over time. If Proxima B remains geologically active, it might maintain an atmosphere, despite ongoing erosion. Its initial composition also matters. Some planets form with large reserves of water and volatile materials, which could sustain them even after long periods of loss. A thick atmosphere, if present, would provide additional protection, absorbing much of the incoming radiation before it reaches the surface. And beyond that, water itself can act as a shield. Even a few meters beneath an ocean surface, life would be largely protected from radiation events above. Taken together, these possibilities suggest a more nuanced picture. The challenges are significant, and in many ways severe, but not necessarily absolute. Whether life could exist there remains an open question, one that depends on factors we are only beginning to understand. Life, if it exists there, may not need to live on the surface at all. It could persist beneath the ground, entirely shielded from the harsh conditions above. On Earth, we already find microbial ecosystems deep within rock, sustained not by sunlight, but by chemical energy. It is possible that similar forms of life could exist on Proxima B, hidden below the surface, unaffected by the constant flaring of the star. Some organisms on Earth, known as extremophiles, can endure levels of radiation far beyond what humans could survive, suggesting that life can adapt in ways that once seemed unlikely. One well-known example is a bacterium capable of surviving radiation doses thousands of times greater than what would be lethal to humans. This reminds us that life, given enough time, often finds ways to endure even the most hostile environments. There is also a more speculative idea that adds another layer to this possibility. Proxima B may once have been very different from what it is today. In one scenario, the planet could have formed with a thick hydrogen atmosphere, more like a small, gas-rich world than a rocky one. This early envelope might have protected the surface from the intense activity of its young star. Red dwarfs, including Proxima Centauri, are thought to be far more active in their early stages, releasing stronger radiation and more frequent flares than they do now. A dense atmosphere could have acted as a shield during this period. Over time, that hydrogen layer may have been stripped away by the star's activity, but by the time it disappeared, the star itself may have become somewhat calmer, leaving behind a rocky world that still retained water and part of its atmosphere. This idea remains uncertain, as no confirmed atmosphere has yet been detected around Proxima B, despite repeated attempts to observe one. So the question remains open. The conditions are undeniably difficult, but not entirely prohibitive. It is possible that life exists there in forms adapted to radiation and extremes. It is also possible that the planet is completely barren, shaped by billions of years of exposure to a restless star. To truly know, we would need direct observations far beyond what we can currently achieve. What we do know is that Proxima Centauri hosts more than a single world. There are at least 2 confirmed planets, and possibly more, each occupying a different region around this small and active star. One of them, Proxima Centauri D, was confirmed in the early 2020s, adding another piece to the system. This planet orbits even closer to the star than Proxima B, at a distance so small that it completes an orbit in just a few days. A full year there would pass in less than a week. Its motion around the star is incredibly rapid, faster than anything seen in our own solar system. In terms of size, it is much smaller than Earth, closer to a scaled-up version of Mars, with too little gravity to hold a thick atmosphere for long. Positioned so close to the star, it lies far inside the habitable zone, where temperatures would be far too high for liquid water to persist. Whatever conditions exist on its surface, they are unlikely to support life. Yet its presence tells us something important. Even in a system shaped by intense radiation and complex gravitational forces, planets can still form and remain in orbit. The presence of multiple rocky worlds around Proxima Centauri suggests that, despite the system's complexity and the star's intense activity, conditions still allowed solid planets to form and persist. There is also a possible third planet, often referred to as Proxima Centauri C, though its existence remains uncertain. If it does exist, it would be significantly larger than the other known planets, with a mass estimated at several times that of Earth, placing it in the category between super-Earths and smaller gas-rich worlds. At that size, it may not be purely rocky. Instead, it could hold a thick envelope of gas, more similar to a scaled-down Neptune than to Earth. Its orbit would place it far from the star, well beyond the region where liquid water could exist. At such a distance, temperatures would drop to extremely low levels, and any atmosphere would likely consist of lighter gases and frozen compounds rather than the mix we find on Earth. Its long orbital period, taking several years to complete a single path around the star, makes it difficult to confirm. The subtle motion it induces in the star unfolds slowly, requiring extended observations. Some studies suggest evidence for its presence, while others argue that the signal may simply be the result of stellar activity mimicking a planetary effect. For now, it remains an open question. There may be more planets in the system still waiting to be discovered. The techniques we use to detect them have limitations, and certain types of planets, depending on their size or orbital orientation, can remain hidden. What we currently know may represent only a small part of a larger planetary system. The brighter stars, Alpha Centauri A and B, present their own challenges. Detecting planets around them is more difficult because their surfaces produce natural variations in light that can mask the subtle signals of orbiting worlds. This makes it harder to separate the influence of a planet from the activity of the star itself. In the early 2020s, astronomers reported a possible planet around Alpha Centauri A using a different approach, one that attempts to directly capture light from the planet rather than infer its presence indirectly. If confirmed, this object would lie within the habitable zone of a star very similar to our Sun, offering conditions far more stable than those around Proxima. However, later analysis raised doubts. Observations at this level of precision are extremely difficult, and false signals can appear even in carefully controlled data. As a result, this candidate remains unconfirmed. Even so, theoretical models suggest that stable regions do exist around both Alpha Centauri A and B, where planets could orbit safely. Around Alpha Centauri A, planets could remain in stable paths within a few astronomical units, covering the entire region where liquid water might exist. Around Alpha Centauri B, similar stability exists closer in, still encompassing its own habitable zone. These findings keep the possibility alive. Somewhere within this nearby system, there may be worlds more Earth-like than anything orbiting Proxima Centauri, places where conditions are calmer and where life, if it arises, might not face the same challenges. For now, we can only observe, refine our instruments, and wait for the moment when the next layer of this neighboring system reveals itself. The relative closeness of the Alpha Centauri system makes it one of the most important targets for studying exoplanet atmospheres. At a distance of just over 4 light-years, any planets there can be examined in far greater detail than those orbiting more distant stars. Instruments like the James Webb Space Telescope are already capable of analyzing planetary atmospheres using spectroscopy, a method that studies how light interacts with matter. When a planet passes in front of its star, a small portion of the starlight filters through its atmosphere. Different gases absorb specific wavelengths, leaving subtle patterns in the light that reaches us. By studying these patterns, scientists can begin to identify what the atmosphere is made of. Future ground-based observatories, with mirrors spanning tens of meters, will extend these capabilities even further, potentially allowing us to directly observe planets around Alpha Centauri and analyze the light they reflect. Among the most intriguing targets in such studies are what scientists call biosignatures, gases that could indicate the presence of life. Oxygen is one of the most important. On Earth, oxygen persists in the atmosphere only because living organisms continuously produce it. Without life, it would quickly react with surface materials and disappear. Methane offers another clue, as much of it on Earth is generated by biological processes. Detecting both gases together, in the right balance, would be especially compelling, as it would be difficult to explain without some form of ongoing biology. If such evidence were found in the Alpha Centauri system, the implications would be profound. It would mean that life has emerged not just once, but at least twice within our local cosmic neighborhood. The question of whether we are alone would shift from speculation to certainty. Such a discovery would influence science, philosophy, and culture in ways that are difficult to fully anticipate. And beyond that, it would reshape how we think about the galaxy itself. The Milky Way contains hundreds of billions of stars. If even a small fraction of them host life-bearing worlds, then the universe may be far more alive than we have ever imagined. The planets around Alpha Centauri offer perhaps our best opportunity to explore this question. They are close enough to study in detail, and the system is old enough that life, if conditions allow, could have had time to emerge. Proxima B might be a harsh, radiation-battered world, or it might shelter life beneath oceans or within its crust. The brighter stars. Alpha Centauri A and B could host calmer, more Earth-like planets that we have yet to detect, or their habitable zones might remain empty. At present, we can only observe, refine our tools, and wait for clearer answers. Reaching these worlds remains far beyond our current capabilities. The distances are immense, the challenges significant, and yet, despite everything, the effort has already begun. The idea of traveling to Alpha Centauri no longer belongs only to imagination. Scientists and engineers are exploring ways to cross that vast distance, even as it stretches across tens of trillions of miles, a gulf so immense that even light requires years to traverse it. Every calculation, every comparison, every attempt to grasp its scale leads us back to the same quiet realization. Alpha Centauri remains unimaginably distant. And yet, throughout history, humanity has shown a tendency to question what seems impossible. Barriers that once appeared absolute have often been redefined. The sound barrier was once thought unreachable until Chuck Yeager crossed it. Flight itself was considered beyond reach until Wright brothers demonstrated otherwise. The moon remained out of reach until Neil Armstrong stepped onto its surface. Now, similar thinking is being applied to the stars. Scientists and engineers are no longer speaking only in terms of distant millennia. Some are beginning to design missions that could reach Alpha Centauri within decades, within a single human lifetime. The idea is extraordinary. The distances involved are far greater than anything humanity has ever attempted. The required technologies are still in development. The risks are immense, and yet the effort continues. Around the world, research teams are working through the challenges. Funding is being committed. Physicists are examining what the laws of nature truly allow, rather than what current engineering can achieve. The attempt to reach our nearest stellar neighbor has quietly begun, even if success remains uncertain. In the mid-2010s, one of the most ambitious proposals emerged. Breakthrough Starshot was introduced with support from Yuri Milner and the physicist Stephen Hawking. The concept aimed to send extremely small spacecraft toward Alpha Centauri at a significant fraction of the speed of light. At such speeds, the journey could take only a few decades, allowing those involved in the mission to potentially witness its results. The idea relies on a different approach to propulsion. Instead of carrying fuel, these spacecraft would use light itself. Ultra-thin reflective sails would be pushed forward by powerful laser beams directed from Earth. Even though photons have no mass, they carry momentum, and when they strike the sail, they transfer that momentum, gradually accelerating the craft. This concept avoids one of the fundamental limits of traditional propulsion, where carrying fuel adds mass, which then requires even more fuel to accelerate. By removing onboard fuel entirely, the system becomes far more efficient in principle. But the engineering challenges are immense. The laser system would need to produce enormous power, concentrated into a precise beam that remains stable across vast distances. The sails would need to be incredibly light, far thinner than any conventional material, yet strong enough to withstand intense radiation pressure. It is an idea that stretches the limits of what we can currently build, and yet it represents something important, a willingness to explore, even when the destination seems impossibly far away. Because even at tens of trillions of miles, even across a gulf that light itself takes years to cross, the question remains, what lies there, and could we ever truly reach it? The sails themselves would need to be almost impossibly thin, measured not in millimeters, but in nanometers. During acceleration, the forces involved would be extreme, reaching tens of thousands of times Earth's gravity for several minutes. In that brief window, the spacecraft would go from rest to a significant fraction of light speed, faster than it takes to watch a single episode of a show. Any component unable to endure that stress would fail instantly. The spacecraft, often described as tiny star chips, would weigh only a few grams in total. And yet, within that minimal mass, They would need to carry cameras capable of imaging distant planets, instruments to measure radiation and magnetic fields, and communication systems strong enough to send data back across more than 4 light-years. They would also need a power source capable of operating over decades. Each of these requirements alone pushes beyond what current technology can reliably achieve, and combining them into something so small remains an ongoing challenge. By the mid-2020s, the reality of the project began to reflect the gap between vision and execution. Progress continued, but more slowly than initial announcements suggested. Funding did not fully translate into large-scale hardware development, and much of the work remained theoretical or incremental. This does not mean the idea has failed, only that it exists at the edge of what is currently possible. There have been meaningful advances. Researchers have begun developing ultra-thin light sails, some only a few hundred nanometers thick, designed with intricate structures to reduce mass while maintaining reflectivity. These designs represent real steps forward, even if the full system remains far from realization. Beyond acceleration, the challenges multiply. The sail must survive not only the initial forces, but also intense heating from the laser beam, and then endure years of travel through interstellar space. That space, while mostly empty, still contains traces of gas and microscopic particles. At ordinary speeds, these pose no threat, but at a significant fraction of light speed, even a single atom carries enough energy to cause damage. Over the course of a decades-long journey, countless such impacts would occur. Simulations suggest that forward-facing surfaces could gradually erode, raising concerns about whether such delicate structures could survive intact. One proposed solution is not to rely on a single spacecraft, but to send many. If most are lost along the way, a small number might still reach their destination. This approach introduces its own complexities. Launching hundreds or even thousands of tiny probes means scaling up every aspect of the mission, from manufacturing to tracking and communication. Each one would need to function independently, increasing both cost and coordination challenges. And then there is communication itself. Any signal sent from Alpha Centauri would take more than 4 years to return to Earth. There can be no real-time control, no direct intervention once the journey begins. Every action must be pre-programmed or handled by onboard systems capable of making decisions without human input. In a sense, such a mission would not just be an act of exploration, but an act of trust. Trust in engineering, in physics, and in a design that must operate alone, far beyond our reach, carrying with it a small piece of human curiosity across the vast darkness between the stars. Sending data back from something so small across 4 light-years begins to press against the limits of physics itself. Radio signals weaken with distance, fading according to the square of how far they travel, for a transmitter operating on such a tiny power budget. The signal arriving at Earth would be incredibly faint. Detecting it would require receiving systems of enormous scale, antennas stretching across vast distances just to capture a whisper of information. Even then, the data would arrive slowly. Images that move instantly between devices on Earth would take hours, perhaps days, to transmit across interstellar space. A successful mission might return only a small amount of information, a handful of images, a few measurements, enough to confirm that the journey was completed and that the instruments survived. Each challenge invites a solution, and each solution introduces new difficulties. The path from current technology to functioning interstellar probes is not a single breakthrough, but a long sequence of incremental steps, each one uncertain. While ambitious concepts capture attention, more grounded efforts are already taking shape, focusing on what can be achieved in the near future. One such effort is the Toliman mission. Rather than attempting to travel to Alpha Centauri, it aims to study the system from orbit around Earth. Its goal is simple in concept, but powerful in implication: to search for planets around the 2 bright stars using precise measurements of their motion. The method relies on a subtle optical effect by analyzing how starlight interferes through a specially designed lens. The telescope can detect minute shifts in a star's position. If a planet is present, its gravity will cause the star to move slightly, and this motion can be measured over time. The instrument itself is relatively small, far more modest than many large observatories, but its design allows for a level of precision that would be difficult to achieve from the ground. Operating above Earth's atmosphere, it can observe continuously, free from distortion, building up a detailed picture of the system over years. If planets similar in mass to Earth exist within the habitable zones of Alpha Centauri A or B, this approach could reveal them. Efforts like this matter because they shape what comes next. Discovering a potentially habitable world around one of these sun-like stars would change the nature of the question entirely. Instead of asking whether such planets exist, we would begin asking how soon we might reach them. Compared to Proxima Centauri, the environments around Alpha Centauri A and B are far calmer. These stars produce far less intense radiation, making their habitable zones more stable and more familiar. A planet in such a region would face fewer of the challenges that complicate the picture around Proxima B. If such a world were confirmed, it would provide a compelling reason to pursue the immense effort required for interstellar travel. The goal would no longer feel abstract, but specific. Not just a distant star, but a particular world, orbiting a nearby sun. And so, alongside the more ambitious visions, these quieter missions continue. They observe, measure, and refine our understanding, bringing the distant system into sharper focus, step by step, as we consider what it might take, one day, to cross the space between. There are many ideas for reaching Alpha Centauri, each balancing what is physically possible with what can realistically be built. One of the earliest serious proposals was nuclear pulse propulsion, explored in Project Orion during the mid-20th century. The concept was direct in its approach. A spacecraft would be pushed forward by a series of controlled nuclear detonations behind it, each explosion driving a wave of plasma against a large plate, steadily accelerating the craft. From a purely physical standpoint, the idea is sound. Calculations suggest such a system could reach a small fraction of the speed of light, reducing the journey to Alpha Centauri to around a century. It does not rely on unknown physics, only on engineering at a scale never attempted. But the obstacles are not technical alone. Launching large numbers of nuclear devices into space would conflict with international agreements, and the risks involved would be difficult to accept. Even if feasible in theory, it remains unlikely in practice. Another concept, often discussed for its efficiency, is antimatter propulsion. When matter and antimatter meet, they convert entirely into energy, making this reaction the most efficient known. In principle, a spacecraft using antimatter could achieve extraordinary speeds, potentially reducing travel times to decades. Yet here, reality intervenes. Antimatter is produced only in extremely small quantities, measured in fractions of a gram. At facilities like CERN, the cost of producing even tiny amounts is immense, and scaling this to the levels required for propulsion would demand resources far beyond anything currently possible. For now, it remains an idea grounded in physics, but far removed from implementation. There have also been more recent proposals that aim for intermediate solutions. Some concepts combine solar sails with powerful laser systems, seeking to accelerate spacecraft to a meaningful fraction of light speed. Under such a design, a mission launched in the later part of this century could arrive at Alpha Centauri within a few decades, allowing those who initiated the mission to witness its outcome. But even these ideas face the reality of funding and priorities. Space agencies must focus on nearer goals, such as returning to the Moon or exploring Mars. Interstellar travel requires commitments that extend beyond political cycles and even beyond lifetimes. At the other end of the spectrum are slower, more achievable missions. Advanced propulsion systems could eventually send probes outward at speeds far greater than those we use today, yet still far below the speed of light. At such velocities, the journey would take thousands of years. The spacecraft would arrive, eventually, but the people who launched it would not be there to see it. This raises questions that extend beyond engineering. Who would support a project that spans such immense stretches of time? What institutions could endure long enough to receive the data? Would the knowledge still hold meaning after so many generations? There is, perhaps, one quiet parallel in human history: the construction of great cathedrals, where builders devoted their lives to structures they knew they would never see completed. The work continued across generations, guided by a shared vision that extended far beyond any single lifetime. And so, in contemplating journeys to the stars, we are not only exploring physics or technology, we are also exploring the limits of human patience, imagination, and the willingness to begin something whose end we may never witness. The motivation behind those vast cathedral projects was rooted in belief rather than science. Yet, they reveal something important. Humans are capable of committing to goals that extend far beyond a single lifetime. Whether we can summon that same level of dedication for interstellar exploration is still uncertain. The slow progress of projects like Breakthrough Starshot highlights a deeper challenge that goes beyond engineering. These missions demand continuity across time spans that our institutions are not built to sustain. Political systems operate on cycles of only a few years, shaped by elections and short-term priorities. Leaders are often driven to focus on results that can be seen within their time in office, not on outcomes that may take decades to appear. Economic systems follow a similar pattern, favoring returns that arrive within years rather than generations. Scientific work faces its own constraints. Researchers build careers on measurable results, publications, and discoveries. A project that yields data long after its contributors are gone offers little direct incentive within the current structure. Funding bodies also tend to support work that produces outcomes within limited timeframes, often just a few years. Interstellar missions do not fit within these frameworks. The required technologies are still emerging. Development could take decades, and success is not guaranteed. The scale of investment would exceed the capabilities of any single nation, and the timeline stretches beyond the stability of most institutions. Every space mission so far, even the most ambitious, has operated within a timescale we can understand. Journeys to the moon, robotic missions across the solar system, even large observatories, all begin and end within a human context. Reaching another star belongs to a different category entirely. The closest historical comparison may be the construction of great cathedrals, projects that unfolded over generations. Some took decades, others stretched across centuries. The people who began them knew they would never see the final result. Yet the work continued. What sustained those efforts was a shared purpose that extended beyond individual lives. The question now is whether a similar sense of purpose can exist for exploration. Can a goal rooted in curiosity and discovery inspire the same long-term commitment? The answer to that question may determine whether humanity ever reaches the stars. And yet, despite all these challenges, the potential rewards remain extraordinary. If we were to reach Alpha Centauri, the impact would extend far beyond a single achievement. It would reshape our understanding of the universe and our place within it. For the first time, we would observe another star system from within, not as a distant point of light, but as a place. Every observation we have ever made has been from within our own solar system. Even our most powerful telescopes can only capture limited detail across such vast distances. A spacecraft at Alpha Centauri could change that completely. It could photograph planets directly, analyze their atmospheres, measure magnetic fields, and study their environments in ways that are currently impossible. Questions that remain open today would finally have clear answers. Does Proxima B still hold an atmosphere after billions of years of stellar activity? Is there liquid water, either on its surface or hidden beneath it? Are there any signs, however subtle, that might suggest the presence of life? If planets exist around Alpha Centauri A or B, they could be studied as well. Worlds shaped by a binary star system may reveal forms of planetary evolution we have never seen before. Much of what we understand about planet formation comes from studying a single example, our own system. Observing another, especially one so different, could transform those theories entirely. In the end, the journey to Alpha Centauri is not only about distance, it is about extending human understanding beyond its current limits, step by step, even when the path ahead remains uncertain. Alpha Centauri offers something more than just proximity. It provides a natural laboratory, a place where our theories about planets and stars can be tested under conditions very different from our own system. Reaching it would not only answer questions about that specific system, it would reshape entire fields of science. The technologies required for such a journey would not remain confined to space exploration. Efforts to miniaturize spacecraft down to gram scale would drive advances in electronics, medicine, and robotics. Improvements in laser systems would influence communication, manufacturing, and energy transmission. Autonomous systems capable of operating independently for decades would transform how machines function across many industries. History suggests that ambitious space programs often produce benefits far beyond their original goals, as seen in earlier efforts that quietly reshaped modern technology. But beyond the technical gains lies something deeper. Reaching another star would mark a turning point in human history. For the first time, humanity would no longer be limited to a single stellar system. Every achievement we have made so far has taken place within the boundaries of our sun's influence. Crossing that boundary would change how we understand ourselves. It would not make the galaxy easy to explore, but it would show that it is, at least in principle, reachable. Alpha Centauri would become a first step, a gateway rather than a destination. The knowledge gained from such a mission would carry forward, making each future attempt more achievable than the last. And yet, even with that progress, a quiet truth remains. Alpha Centauri is the closest possible target. Beyond it, the scale expands dramatically. The Milky Way contains hundreds of billions of stars spread across distances so vast that even light takes tens of thousands of years to cross them. Our nearest neighbor lies just over 4 light-years away, while the center of the galaxy is tens of thousands of light-years distant, and the far edge stretches even farther still. If reaching Alpha Centauri requires decades at extraordinary speeds, then traveling to more distant stars quickly becomes a question of centuries, millennia, or longer. Even a spacecraft moving at a significant fraction of light speed would need hundreds of years to reach stars 100 light-years away, and thousands of years for more distant regions. The limitation is fundamental. The speed of light appears to be a boundary that cannot be surpassed. Concepts that attempt to bypass it remain theoretical, without experimental evidence to support them. And even if such ideas were possible, the energy required would be immense, perhaps beyond anything we could realistically produce. This creates a universe that is vast, structured, and quietly isolating. It also offers one possible explanation for something we have long wondered about: the question of why we do not see evidence of other civilizations, often referred to as the Fermi paradox, may not require rare life or hidden signals. It may simply reflect distance. If intelligent life arises elsewhere, it faces the same reality we do: The same immense separations, the same limits imposed by physics. Each civilization, if it exists, may be confined to its own region, separated not by choice, but by the structure of the universe itself. And so, as we look toward Alpha Centauri, we are not only looking outward, we are also beginning to understand the deeper nature of the cosmos, a place of possibility, but also of distance, where even the nearest neighbor reminds us just how far apart everything truly is. 4 light-years to the nearest star, then hundreds of light-years to reach larger stellar groups, and tens of thousands to cross the galaxy itself. Even a civilization far older and more advanced than ours would still face the same underlying limits of space and time. Perhaps they could slowly expand outward, reaching nearby systems over immense stretches of time, but the galaxy remains vast, even traveling at light speed. It would take 100,000 years to move from one side to the other. It is possible that every intelligent species eventually encounters this same boundary. A few nearby worlds may be within reach. Given enough patience and effort, most will remain forever distant. The galaxy begins to resemble a chain of isolated islands, each separated by oceans too wide to cross. In that sense, Alpha Centauri becomes the first distant shore beyond our own, and it reflects a deeper paradox. This nearby system is close enough that we have studied it in remarkable detail. We know the masses of its 3 stars. We have confirmed planets around at least one of them. We have even identified worlds that might, under the right conditions, support life. And yet, between us and that knowledge lies an immense gulf of empty space. We can describe it with precision, but we cannot reach it. That tension exists everywhere in the universe. Our instruments allow us to observe galaxies billions of light-years away. We detect signals from the earliest moments after the beginning of the cosmos. We map structures on scales that stretch across unimaginable distances. And still, we remain here. The universe allows us to see, but not to travel freely within it. Alpha Centauri becomes a kind of test. If we can find a way to cross that distance, then perhaps the next step becomes possible, and the one after that. Over time, those steps might extend outward, slowly carrying human presence or human machines deeper into the galaxy. But if the barriers remain absolute, then our existence will always be confined to this one system. In that case, the Sun and its planets are not the beginning of our journey, but its full extent. Everything beyond remains permanently out of reach. And yet, the act of trying still matters. It reveals something essential about us. We emerged on a small world, orbiting an ordinary star, in a quiet corner of a vast galaxy. Nothing in that origin required us to imagine traveling between stars. And still, we do. We design sails that ride on light, build systems that might one day guide machines across interstellar space, and calculate paths toward destinations we cannot yet reach. The ambition itself carries meaning, whether or not it succeeds. 4.37 light-years, tens of trillions of miles. A system of 3 stars bound together across spans of time far beyond human experience. Worlds that may or may not hold the conditions for life, illuminated by different kinds of starlight, shaped by forces both gentle and extreme. And somewhere within that distance lies the quiet question that continues to guide us. Journey times stretched into spans that resemble geological eras if new technology does not emerge. What feels close in cosmic terms remains profoundly unreachable in practice. It is a kind of proximity that tempts us with knowledge, yet keeps that knowledge just beyond our grasp. Alpha Centauri becomes both a destination and a boundary. A place that represents either the beginning of interstellar travel or the edge we may never cross. It is, at the same time, our nearest neighbor and one of our greatest challenges. A quiet test of whether the universe can ever become something we truly explore, rather than something we only observe from afar. Its true scale brings together everything we have considered. The immense distances that reduce even our fastest machines to near stillness. The three stars bound together in motion for billions of years. The planets that exist under conditions we are only beginning to understand. And the missions that may one day attempt to bridge the space between. To understand that scale is to see ourselves differently. We are a single species on a single world, orbiting one star among hundreds of billions in a galaxy that is only one among countless others. Even the closest star lies beyond our immediate reach. Most of the universe will remain inaccessible, no matter how far our technology advances. And yet we continue. Scientists continue to design. Engineers continue to solve. Ideas continue to form. Even in the face of uncertainty, the effort does not fade, even when the obstacles seem overwhelming. Alpha Centauri simply remains there. It has existed for billions of years and will continue to do so long after us. The question is not whether it will change, but whether we will find a way to reach it. In that sense, its scale reveals two truths at once. It shows how small we are within the universe. And at the same time, it reveals something equally remarkable. We are part of that universe, and we are trying to understand it. Among all the stars, all the galaxies, all the matter scattered across space, there exists a small place where the universe has become aware of itself and has begun to ask questions. We are that place. We are the part that looks outward, the part that continues to reach, and Alpha Centauri stands as a quiet marker of where that reaching might one day lead. The first step towards something far larger, in a cosmos that extends far beyond what we can fully imagine. 4 light years to the nearest star.